Assalamu alaikum everyone. Today we have to start this new topic which is about the estimation of the purchased equipment cost. And we know that to estimate the cost of equipment, we can follow different methodologies. Number one methodology that we can follow is to get the quotation from the vendor. So we have to get the vendor quotation. It could be the most accurate technique based on the specific information and requires significant engineering. So you provide some specific information about the equipment to the vendor, and then he can provide you some of the cost details, and it requires significant engineering. So when you supply an information to the vendor, you would provide all the engineering information. So whatever the data that you get from the vendor, it should be accurate in terms of cost. The second way of getting the cost for the equipment, use previous cost on similar equipment and scale for time and use. And it can be less accurate. Beware of large extrapolation. Beware of foreign currency. Okay. So the other technique that we can use to get the cost of the equipment is to compare the cost of the same equipment when it is installed in some industry or in some plant. Okay, then you will see that what is the time change, what is the current time, and what was the time at which that equipment was like installed in the other industry, what is the current capacity, and what was the capacity of that plant. Okay, so we will see some of the formulas in this area today to get the cost estimate. Okay, use cost estimating charts and scales for time. The third more convenient way is to get the estimation about the cost using some kinds of charts relevant to each of the equipment, to each of the industry maybe. Okay, and it will give you the information on the scale of time. Okay, so you can have some information that the time with the increase in the time, in the increase in years, what could be the impact on the cost. So basically it will include the inflation and like the current values of the equipments, and how the current inflation can impact the cost of equipments that were earlier installed in some other industries. Okay, so we will see this one in detail today. Now, this is an equation that is mostly used in the chemical engineering processes to estimate the cost of any equipment and even the cost of any plant also. So this equation is basically representing you the effect of size or the capacity. So the size and capacity, it is the same thing here. Now CA, it represent you the cost of the new equipment. CB, it represent you the cost of the same equipment but in the previous time, or that has been purchased earlier. Okay, AA, it represent you the cost of new equipment. AB, it represent you the cost of the equipment that was purchased earlier. Okay, and N represent you the cost exponent. Okay, so we will use this equation to estimate CA, the cost of new equipment, based on the capacity of the new equipment and the old equipment, and we have to compare that one with the cost of the same equipment but in the earlier years. Okay, now here, if you rearrange this equation, you will bring CB on the right hand side, so it will be in this form. Okay, you will multiply the CB on the right hand side and then CB divided by ABN. So you will separate the cost of this equipment and compare it with the capacity here. So we can have a new factor K, that is equal to CB by ABN, and the new equation that you get here, CA, it will be equal to K and AAN. Okay, so you would be having the same equation here, but we have just introduced one new parameter here, which is K, and that represent you the cost of equipment along with the capacity of that equipment that was installed in the earlier years. Okay, so this is a new equation that we will use to estimate the cost of the equipment. Okay, so maybe you can use this equation also, or you can use this equation. The information is same. Okay, so now let's see how we can actually read some of the charts here. For example, you are dealing with some kind of centrifugal air blower, and the information that you would have here, it would be the volumetric flow rate of the air through the compressor, and on the left hand side you would be having the purchase cost of equipment. Okay, so you would see that as the volumetric flow rate of the air through the compressor, it is increasing, the size of that compressor would increase, and then you would see that what should be the impact on the cost of that equipment. Okay, so you can maybe at 10 standard metric cube per second, you would go upside this one, you would reach at this line, and here you would see what should be the cost here. Okay, and n here it represent you the exponential factor. Okay, so we will see that what is this n here, like in this equation, n represent you the cost of exponent. Okay, so this value for n, it is basically specific for different equipments and even for the plant. So let's see this one here. For example, if you are using some kind of reciprocating compressor, and the capacity of that compressor, it varies from 0.75 to 1490, then the cost exponent can be used as 0.84. If we are using some kind of heat exchanger with this capacity, then the value of n can be 0.59. Similarly, if you are using some vertical tank, centrifugal blower, jacketed cadet glass line, so you can see the capacity here, and then you can here see the cost exponent. So what we see here, the minimum cost exponent, it can be 0.30, and the maximum value it could be 0.84. Okay, so from here what we can see here, the value for the exponent, it can vary from zero point 0.6 to 0.84 typically. However, now sometimes we use the average value for n. The value of n can be zero point 0.6 here. Okay, sometimes we use the value zero point 0.6, and then we call this one as a 6/10 of the rule. Okay, now 6/10 of rule is defined as an equation if you are using the value for n to be zero point 0.6 here. Okay, so this is a key here. Assume all equipments have n equal to zero point 0.6 in a process unit and scale up using this method for the whole processes. Okay, so we can sometimes make the analysis more easy to estimate the cost, and we use the zero point 0.6 as a value to estimate the cost of the new equipment. Okay, order of magnitude estimate. So order of magnitude, you have to see what is the capacity of the old plant and what is the capacity of the new plant and what should be the value for exponent. Now let us solve this example. Use the 6/10 rule. Now 6/10 rule means that the value for n, it should be 0.6 to estimate the percentage increase in purchase cost when the capacity of a piece of equipment is doubled. Now what we see here, the capacity of the equipment is doubled. Okay, so you can see this equation here, which is a replica of this equation. Okay, now the capacity of the equipment is double, so it will become 5 by 1, and on the left hand side you have CA by CB. Value for n, it should be 0.6 for the 6/10 rule. So you can see here CA by CB. Here the capacity it is double, so 2 by 1, and zero point 0.6, it is the 6/10 rule. And the new value and the ratio between the new capacity and the old capacity, it comes out to be 1.52. Now here you can calculate what should be the increase in percentage, and 1.52 minus 1 divided by 1 multiplied by 100. So you would see that if the cost of the equipment, if the size of the equipment is double, then the cost is not doubled, it only increased by 52%. So what we see here, that the cost increase, it is not linearly increase with the size of the equipment, right? So therefore here you would see that there is a special impact on the value for the exponent cost. Okay, so for this equipment, the size of the equipment is double, but we see that there is an increase in the cost up to 52%. Okay. Now, what is a conclusion that we can see here? The larger the equipment, the lower the cost of equipment per unit of the capacity. So, with the increase in the size of the equipment, the cost is not linearly increased. Okay, so it will slightly increase. Now let us solve another example 7.4. Compare the error for the scale up of the reciprocating compressor by a factor of 5 using 6/10 rule in place of the cost exponent given in the table 7.3. Okay, now we here we are provided the two things. First thing that we need to consider here, it is the 6/10 of the rule. So the value for the n, it can be 0.60. Okay, and then the scale up information is provided here. So the scale up is 5. So the value that you can use here for A by AB. So new value, new capacity by old capacity, it is 5 times. So 5 by 1 with the value 0.6. Okay. So we can see here the value for n is 0.6. This one AA by AB, it is 5, and then the value for n, it is 0.6. So the new cost, or the ratio between the new and the old cost, it comes out to be 2.63. Okay. Now if we are comparing this 6/10 rule with the actual capacity factor, or the exponent that is provided to you in the table, now what could be the new cost ratio? Okay. Now we are using the reciprocating compressor. Okay. You would go back here, and here you would see for the reciprocating compressor, the value for exponent, it can be 0.84. Okay. So we can use this new value to estimate what is the difference in the new cost and the old cost in terms of the ratio. Okay. So with the same thing, the capacity is 5 by 1, and now we are using the new value for the exponent, and the new cost ratio, it comes out to be 3.86. Okay. Now we would see that what is an error percentage. Okay. So you would use this one, 2.60 minus 3.86 divided by 3.86, and you would see that there is a reduction in minus 32%. So what we see here, that by changing the values for these exponents, the value or the cost of the new equipment, they can be changed. Okay. So here we are just like trying to see that what could be the percentage error if we change the exponent values. Okay. Now how we get these exponent values in detail, let's see this one. For example, we are having this volumetric flow rate of the air on this line, and on the left hand side we are having this value here for the purchased equipment. So you would see this one here. You would see the capacity of the compressor, and then you would touch this line, and then on the left hand side you would see what is the cost. Okay. Now this line, where do we get this line? We will see in detail, and basically it comes out with the inflation. Okay. So we will see that how we see get these lines. Okay. And let us solve one more example here. The purchase cost of the recently acquired heat exchanger with an area of 100 meter square was $10,000. Okay. Determine the constant K in the equation 7.2. The cost of new heat exchanger with an area equal to 180 meter square. Now we are provided with some of the information that the heat exchanger area, it is 100 meter square, and the cost was $10,000. Now we have to estimate what is the value for K. Now for the value for K, what we see here, the equation that we have seen earlier, that is equal to CB divided by AB. Now CB is the old cost, AB is the old capacity, N is the value, that is an exponent here. So we have to see this one. For example, if we are using the heat exchanger, so we would go back to the heat exchanger table here. Okay. Heat exchanger, shell and tube, carbon steel. So you would see the value of the exponent here. Okay. So you can use this value for the n here in your equation. N is equal to 0.59, and then you would put the information in this equation to estimate the value for K. So the value for K, it comes out to be $661 per meter square. Okay. Now you would use this value for K to estimate the cost of new heat exchanger with an area of 180 meter square. Now CA, it is the new cost, the new capacity that is provided to you, 661, and then this one is the value for K that we get here, $661 per meter square, and then we can have the new value for this, the new heat exchanger area or the capacity, and the value for N we have already calculated. So the value for the heat exchanger, it comes out to be 14,100. Okay. So simply we have just like break down this main equation into two parts. Okay. First we evaluate the value for the K, and then we evaluate the value for the CA. Okay. So you can use directly this equation also, or you can just find out the value for the K1, K first, and then you can find out the value for CA. Okay. Okay, now here the new value for this heat exchanger, it comes out to be 14,100. Now this concept basically only applies to the economy of the scale. If the size of the equipment changes, now how it would impact the cost. Okay. But until now we didn't include the the part for the inflation. Okay, now we have to see that if you have purchased some equipment maybe 10 years back, now after 10 years or 5 years, what would be the value? Or you have some cost of some pump in the year 2000, now what would be the cost of that equipment in the year 2018 or 2019? Okay, so there we have to include the concept of the inflation also, so we will see that one also. Now, let us see what is an effect of the time. Time increases, cost increases. Okay, so we can see that with the time, with the increasing number of years, the cost of the equipment increases due to the inflation. Now, how we can handle this inflation here? Inflation is measured by the cost indices. Okay, so we have developed different kinds of cost indexes uh, that can link the inflation and with the cost of the equipment. Okay, so there are different cost indexes that we can use. First one, it is the chemical engineering plant cost index, CEPCI. So this index is, it is mostly used in the industries and the academia. Marshall and Swift process industry index, so it is also the type of index that we can use. Okay, so these two indexes basically, it give you the increase in the cost with the increase in the years. Okay, numbers based on basket of goods typical for construction of chemical plants. Both of these indexes basically they develop the values based on the common equipment that we are using in the industries. Okay, so we'll see this one, what it could be the basket of goods in the chemical plants. Now this one is basically the overall criteria. Okay, for example, you want to evaluate or develop some cost index. Now the cost index, it would be just one number. Okay, but that one number would be based on some detailed calculation about these things in the industry. So maybe they have to consider the fabrication cost up to 37%, process machinery up to 14%, pipes, valves, fittings cost 20%, process instruments and controls 7%, pumps and compressors 7%, electrical equipment and materials 5%, structural support and installation paint 10%. Okay, so this makes 100%, but while calculating the cost index, we have to take 61% of this 100%. Okay, so we will take the 61%, 61% of this value to estimate the value for this cost index, and the rest of 39% would be coming from this part: erection and installation labor 22%, building materials and labor 7%, engineering and supervision 10%. So this makes 39%, and overall it will become 61 plus 39, 100%. Okay, so once you have this calculation, then you can basically include each and everything in the industry that is required to develop the cost index of the particular year and how it has been inflated with the previous years. Okay, so what we can see here, there could be a new equation that relates the time effect with the cost. Okay, so for example, C2, it is the new cost of the equipment, C1 is the old cost, and I2 is the cost index of the new year, I1 it is the cost index of the previous years. Okay, so we can use this equation to see that if we have bought some equipment in year 2010, then what would be the value for the same equipment in the year 2015? Okay, so we are just like comparing the cost, but here the capacity we are not including. Okay, so we will see later that how we can include the capacity also in these equations, but for this equation we are using the same capacity of the equipment, but to see the cost of that equipment in different years. Okay, now here what we see here, different chemical engineering cost indexes are given here, that is giving you the information about the inflation. So we see that with the increase in the, so what we can see here, with the increase in the number of years here, there is an increase in the inflation in all of these indexes. Okay, so if you can take any of the index, so what is a general thing that we can see here, there will be an increase in the inflation that would impact the cost of the equipments. Okay, similarly, we do have some kind of these charts in terms of values. So here we are taking the Marshall and Swift equipment cost index, and here we are taking the value for the chemical engineering plant cost index, And here with each of the years here, they have calculated the cost index. Okay, for CEPCI you can see the different numbers here, and here for the Marshall and Swift here you can see different numbers here. Okay, so you can choose any of this one, but it is preferred to go with this CPCI, but you can choose any of this one, because ultimately we have to take the ratio between the 2 years, so the effect of these higher numbers would be negated there. Okay, so we can see this one again with the increase in number of years. So we see that the chemical engineering cost index, it has been like more or less increasing, right? So CEPCI numbers are increasing. So what we see here, with the increase in the number of years, the value of CEPCI, it would be increased due to the increase in inflation. Now let us solve one of the question here and see that how the cost index, it can affect the cost of the equipment. The purchase cost of the heat exchanger of 500 meter square area in 1996 was $25,000. Estimate the cost of the same heat exchanger, so the area would be same, in 2011 using two indices introduced above. Compare the results. Okay, so the area is same and the cost is provided for 1996. That comes out to be 25,000. Now we have to calculate the cost of the same heat exchanger in 2011. Okay, so we took two cost indexes, one from the Marshall and the one from the CPCI. For 1996, we have got these two cost indexes for both of these companies, and then in the year 2011, we also got the cost indexes relevant to each of this company. Okay, now we have this information, and we will use this information to get the cost of the heat exchanger in the year 2011. So according to Marshall and Swift cost indexes, what we see here, the cost index, you can simply see this equation here, the old cost multiplied by the new cost index and divided by old cost index. Okay, so we are using the same equation here. So the cost of the heat exchanger, then we can have the cost index for the year that we are going to evaluate, that is 2011, divided by the cost index of the year in which the price is provided, that is 1039. So we can have this value. According to Marshall and Swift, the cost of the same heat exchanger in 2011, it would be $35,852. Now according to the second cost index, CPCI, what we will do here, we will use the same value for the heat exchanger that actually cost, and the new cost index now for 2011 is here, then the cost index for 1996 is here, and we would find out the value, it should be around $38,089. Now for using these two cost indexes, we can get different values for the heat exchanger. So we will see that new value, it should vary between these two cost indexes. So now what we can do here, we can actually compare the results, and we will take the difference and the average of these two cost indexes. So what we can do here, we can like subtract 35,000 minus 38,089. So we will be having this term in the numerator, divided by, we would take the average. Okay, so we will take this one average here, 35,000 plus 38089 divided by 2. Okay, so we will take the difference and divide it with the average, multiply by 100. So we will get some value for the average difference. So we will see that by using different cost indexes, there could be different percentage error between the results. Okay, so the new heat exchanger, it can vary between these two costs, and the relative difference between using different cost indexes, it could be 7.4%. Okay, now let us solve another question here. Cost of vessel in 1993 CEPCI 359 was $25,000. What is the estimated cost today, September 2003, CEPCI 402? Now we are provided with the old CEPCI, and we are provided with the new cost index 402, and we are provided with the cost of some vessel in the year 1993. So simply we will use the equation cost now, cost in 1993, and index now, index in the 1993. We are using CEPCI cost index, so we will be using the value for the cost index from PCI. So we can have the value here 402 current index, and this one is the previous index multiply, and you can multiply by 25,000, which is the cost of this vessel, and here you would be getting the cost of the new vessel in the year 2003. Okay, so it's simple. Now let us solve this example. Now here we have to compare different things, and it is the more better example. We are provided with the different heat exchangers with different cost and different cost indexes, okay, with a different year, and then we have to find out some different heat exchanger size in different year, okay. So let us see what we have here. Two heat exchangers, one bought in 1990 and the other in 1995 for the same service. So these are the two things that heat exchangers that we are buying in two different times. So a case here, so the area is 70 meters square, time was 1990, cost is $17,000, cost index is 358. For B, the size of the heat exchanger is 130 meters square, time is 1995, cost is $24,000, and the index value is 381. And then we have to calculate the value for the cost in year 203 with the index 50402 and with the new capacity. So we will see that what are the different equations we have to use to get the value for this new cost. Okay, now must first bring cost to the common time. For A here, for the A case, the area for the heat exchanger, it is 70 meters square. Okay, so the cost that we would find here for the year 2003, so we have to compare it with this one 2003. So the value for the heat exchanger, it is 17,000. Okay, then we have the cost index for 2003, that is 402. Okay, this one, and then we can have the cost index for this one, that is 358. Okay, so the new value for the heat exchanger in 2003, it would be $19,089,000. The same thing we have to do it with the second heat exchanger, 130. It is the area of the heat exchanger. The new cost, so you are provided with the cost 24,000. Okay, 24,000. Okay, and this one is the new cost index for 2003 year. This is the cost index that is given here for the year 1995. So the new cost that we would find here for the year 2003, it comes out to be $25,323,000. Okay, now we have calculated the cost in the year 2003 for two different heat exchangers with the different capacities. Okay, now here we are not provided any information about the exponent, so we are trying to calculate the value for the exponent here. Okay, so how we can calculate this is the equation that we have seen earlier. C is equal to KAN. Okay, now what is the C here? This is the new cost, and K is the old cost divided by the old capacity. Okay, and here AN, it represent you the new capacity, and N represent you the exponent. Okay, so this one, the old capacity, which is provided here 19, where is it? Okay, and this one in the current year we have found this capacity to be 19.089. Okay, so we have put this one here. The value of K we don't know. The capacity of the heat exchanger, it is 70 meters square, so we have this one from here. Okay, 70 meter, and the value of N we don't know. Okay, similarly we have to do it with the second case that we have. The cost here for 2003, the value of K we don't know. 130, it is the capacity of the heat exchanger here. Okay, and then we can have this, and then we can have this equation here in this form. Okay, our main purpose is to get the value for this N. Now how you can get the value for N, let us go back to some of the charts here. For example, if we are using some kind of this chart. Okay, now how we are getting this chart here? So on the left hand side we are provided with the value for the cost here in terms of log, And also on the bottom we have the value for the volumetric flow rate in the form of log. Okay, so how you would get this line here. So you would take simply the slope of this line. Okay, so how you would find out the costs or the slope of this line. You would take the difference in on the of the y-axis, and you can take the difference in the x-axis. Okay, so log of cost here on the left hand side, and log of what we have is the capacity in this denominator. Okay, so that's how you will get the value for the slope of this line. So same thing we have to do here. Now here, to get the value for the slope here, you would see that on the left hand side or on the y-axis we are provided with the cost here. Okay, so you would take the log of the cost that we found here for this one for 1995. Then we have the cost here for the year maybe 1990. So you're taking the log of what we have on the y-axis, and then on the x-axis we are provided with the capacity. So you would take the difference of the capacity. So here you would be getting the value for the slope here, that comes out to be 0.4565. Now if you look at this equation again, we can rearrange this equation to get the value for the k here, or the capacity here for the 19.089. an, what is the a here? It is the capacity that was 70 meters square, and the value for n, it is 0.4565. So the value for k that you would find out here, it is $2.745. Okay, so the same thing you can also actually calculate for the second case. Okay, maybe you can take the value for the c to be 25.325, and instead of a you can take 130, and the value for n you can use this one. So the same result you would get for the value for k. So once you have the value for this k here, you would be using this equation back. So you are trying to calculate the new cost of the heat exchanger. So you would use the value for k 2.745, that is here. The new size of the heat exchanger, it is 80 meters square. Okay, it is given here 80 meters square, and then the exponent that you have just evaluated here, it is 0.4565. That comes out to be $20.288. So this cost, it is basically like 20.288. It is you have to multiply this one with 1000, because here we are like using the factor of 1000. Like for example, this 17 here or this 24 here that we are using, it represents you the $17,000 and $24,000. Okay, so the same thing, when you calculate the cost here, you have to multiply this one with the 1000 to get the actual value for the cost. Okay, so maybe it is better that when you calculate here, you would use the actual numbers here. Okay, maybe you can use 17,000 and 24,000. So that would be the new value for CA and CB. So at this stage you don't need to multiply it with the 1000. Otherwise, if you take like different you ignore the units, or you like do not consider 1000 or 10,000, and you just simply write down the numbers, and you have to compensate that effect here. Okay, so this is how we are multiplying this one with the 1000 and just rounding off the figure here. Okay, so the new cost of the heat exchanger with the 80 meters square, it comes out to be $20,290. Now let us solve the last example for today's lecture. The capital cost of 30,000 metric ton per year is for the propanol plant is 1996 was estimated to be $23 million. Estimate the capital cost of the new plant with the production rate of 50,000 metric tons per year in 2011. We are provided with the information about the year, uh, the capacity, and the cost. Okay, and we have to calculate the new cost with the new capacity of 50,000 metric ton, and the year is given here. So what information we don't have currently? We don't have the information about the inflation that we can get from the CEPCI table. Okay, so what we see here, if you look at the formula here, like we are combining different things. We have to see the cost, we have to see the capacity, and then we have to consider the inflation. Okay, so this could be the journal equation that you can use in this regard. Okay, so the old cost we are provided here, that is 23 million. And the new capacity that we have to choose here, what is the new capacity here, that is 50,000 metric tons per day. So you can have the 50,000 metric tons per day divided by the old capacity. We have this one old capacity, 30,000 metric tons per year. Now what is the value for this one? We are using the 6/10 rule of this process or this plant, so we will use the average value of 0.6 instead of this x. Now on the CEPCI, we have to use the CEPCI for the year 2011, and here we have to use the CEPCI for the year 1996. Okay, so we'll see this one for the 2011 and 1996. What should be the value? Okay, for 2011 it is 582, and for the other one, uh, what is in here? Okay, so here 582 it is for this one to 2011, and for 1996 it will be, okay, 1996 it is 382. So you can get this value from this table. Okay, now here you can put this information on this equation here, and the new value for this one, it comes out to be $47.6 million. Okay, so this is the new value for the cost of this propanol plant. Okay, so this equation, you can use this equation. It combine like the cost, capacity, and the inflation together in one part. Okay, and if some information for the capacity is not given, so you can ignore this part and you can use other two parts. Otherwise, I mean, this is the general equation that you can use to compare the capacity, inflation, and the cost together. And we can actually use these equations a lot in the engineering analysis and also in the plant design analysis. Okay, so this is all for today. Let me know if you have any difficulty. Thank you.